presentation than I've done in the past, but we have several key areas to cover and also help you see the big picture. A good hypothesis translates a research question into a testable form. It's an iterative process. What that means is it takes a long time and a lot of work to craft a good working hypothesis. But if you go through the steps, you'll get a very good return on your investment. Many research projects have run aground very quickly because a person failed to go through these steps and tried to take shortcuts. And so if you remember a previous presentation, we said the steps of going through a research project is to observe a phenomenon, develop a research question, which we use in health circles, PICO. We conduct a thorough literature search, and this may mean going back and honing our PICO a little bit, and then we refine it and we create and test a good hypothesis. Also, if you remember, we can't test our hypothesis in the entire population. We have to select a sample from the population to test the hypothesis and then infer our results to the larger population. So we have descriptive statistics and inferential statistics, meaning we infer results from a sample to the population. Also remember that the difference between our model, our sample, and the population is called error. Individual outcome is a sum of the effect plus error. And if we want to reduce error in our model, then we have to increase reliability. We want to assure that the sample that we study represents the population. This is why we do descriptive statistics first. We check the mean, the median, the mode. We look for outliers. We look for skewness. We look for kurtosis. So all of these things are important beginning steps to make sure that we start out a research project on good footing. We also make sure that we select a valid and reliable tool to measure the variable of interest so that we don't have error in our study. So what is a good hypothesis? It's clear and precise. It's capable of being tested. For example, several years ago we wanted to look at our question was, does economics impact or affect prevalence of pediatric obesity? But the first question was, well, how do you measure economic status in a child? They don't really have W-2 forms we can look at. We couldn't use zip code. All the children in our sample lived in 2 different zip codes, and they were both rural. We also found that just because a child is from a poor family, it doesn't mean that child is particularly poor. There are many systems in place to protect children from the effects of poverty. So we really had a difficult time testing this question. We finally did it, but we had to use some clear thinking there. So think about when you do a research project how you're going to test your particular hypothesis. It needs to be specific and limited in scope. Another error many novice researchers make is they go out too broadly, cast a broad net trying to measure something on a grand scale. It's not possible. Our hypothesis needs to be consistent with known facts, and this is where doing a good lit search will pay off. A good hypothesis states relationships between variables. Now, a relationship can be directional, meaning there is a relationship or a difference between 2 variables, or it can be non-directional, meaning there is no relationship between the variables. And we're going to come back to this later on in an example, but please read in your book and make a note of these distinctions in a hypothesis, a directional or a non-directional hypothesis. So a directional hypothesis says there is a difference or a relationship between 2 variables. It is called the research hypothesis, or H1, also known as HA. Make sure you know these descriptors. A non-directional hypothesis states there is no difference or relationship between two variables. It's called the null hypothesis, or H0. Even when we've done our homework, we've developed a great hypothesis and assured we've have a good representation of the population, we've selected our valid and reliable measurement tools, we can never really prove our results because there will always be some error that impacts the outcome. Therefore, we can only test the null hypothesis. All this semester and in your research project, you will test the null. And you will either accept the null or you will reject the null. So it's the benchmark against which study outcomes are measured. It usually states there's no difference or relationship between variables of interest. In other words, the independent variable will have no effect on the dependent variable. If there is a difference or relationship, it was due to chance or error. The researcher looks for sufficient evidence to reject the null. If we can reject the null, then we say that our results were significant, that they did not occur by chance. The alternative hypothesis H1 or HA states there is a direction or relationship difference between variables of interest. Sometimes it may even state the direction of that relationship, and we'll talk about that toward the end of this lecture. Here's a comparison. The null hypothesis of an observation is there is no relationship between serum ammonia level and consumption of branched-chain amino acid protein in patients with end-stage liver disease. The research hypothesis would be there is a relationship between serum ammonia levels and consumption of branched-chain amino acid proteins in patients with end-stage liver disease. Now this is non-directional, meaning we've not predicted what that relationship might be. In other words, if a person consumes branched-chain amino acids, will their ammonia levels go up or down? So if we had a directional hypothesis, we might say diets high in branched-chain amino acids reduce serum ammonia levels in patients with end-stage liver disease. Now, why did I choose a positive direction? It's because if I read some research articles on this, there are some studies that suggest patients who consume branched-chain amino acid proteins over the aromatic proteins can have lower ammonia levels. So we can select a direction based on what is known about the subject in the literature. If we don't have any literature to back us up, we have to go with non-directional hypothesis. Let's say that a nurse and a dietitian decide to test the null hypothesis in a hospital population of patients with end-stage liver disease who have elevated ammonia levels. And so we write our null hypothesis and we write our research hypothesis. Every ESLD patient with elevated ammonia levels is placed on a diet that's 60% branched chain and 40% aromatic, and if they're unable to eat by mouth, we'll give them an equivalent tube feeding, such as hepatic aid. And then we'll check the ammonia levels at baseline and again 2 weeks later. At the end of 14 days, we compare the measurements and find that the ammonia levels were quite different between baseline and 2 weeks. But how do we know if our results can be extrapolated or inferred to the whole population of patients with end-stage liver disease? How much error exists between our model and the population? The answer is you can't know. But before you use that hammer, let me assure you that you can make an educated guess at the characteristics of a population from your sample. Some very smart people figured out that if you have a decent sample size, in statistics that means generally more than 30 people in a group, then you can estimate the probability that your sample actually tells you something about the larger population. In other words, you can infer your results to the larger group. Remember how I told you fit a model to the real world, whether an individual or population, by comparing what your model tells you to what it doesn't tell you, or comparing effect to error? Well, that's how it's done. You already know the general form of what I'm about to show you from our previous PowerPoint presentation. If the ammonia levels are different before and after treatment in your sample, then you can make an argument that they may be different in the population. Let's get a measure of our effect. We take the ammonia levels in patients who have consumed a diet high in branched-chain amino acids, and we subtract the baseline ammonia levels. And that gives us our effect size. Our effect. But we still need estimate of our error. How on earth can you measure the error in a population? Those really smart people we told you about figured out that if you took a bunch of samples from a population, the means of all those samples would cluster around the true population mean, that mean that you can't really measure. So let's say we did this study with end-stage liver disease patients hundreds of times, and we had a mean ammonia level at baseline and a mean ammonia level 2 weeks out. All of those means would cluster around the midpoint or the middle. Even better, they discovered that the way those means cluster around the true population mean has a predictable shape. And I'll bet you know what that shape is because you read your book. Also, it has an error that can be estimated by dividing the standard deviation of a sample by the square root of the number of individuals in the sample. Very easy to calculate. The discovery that sample means are spread around a population mean in a normal distribution is called the central limit theorem. Hopefully, you noted this in your text. It allows us to make educated guesses about the likelihood that our sample tells us anything meaningful about the real world. The central limit theorem will tell us if the difference we found in our patients is truly real and can be inferred to the whole population. We calculate the error of the sample means around the population mean simply by dividing the standard deviation of our sample by the square root of the number of individuals in our sample. So in order to figure out whether the effect in our sample applies to the population, we just put the effect over error. This is known as a z-score. It can be more generally written without the branched-chain amino acid example as you see here on the screen. Now, one more step and we're there. We've got our effect and error score for the difference between the two means, which in this case is our z-score. Now we can use the z-score to figure out how likely it is that our finding is a real finding and not simply by chance. I told you one of the features of the central limit theorem is that it states the sample means are distributed around a population mean in a normal fashion. We will use this property to figure out the probability that our sample is real. So we have the shape of the normal distribution that we talked about in descriptive statistics. The z-score is a bit like an address on that normal curve. A z-score could fall just by chance toward the outside of the distribution, but this is not very likely. If our z-score does fall in these extremes, we know that means it's probably not by chance. It's probably because of something that our test proved. So if the difference between the means of our two groups has a z-score greater than 2 or less than -2, this would mean that the means of our two groups are far apart on the normal curve. It would mean that it would be very unlikely they were from the same population, or the two groups is large enough that our study impact made a difference. To put it another way, with a large z-score, You can be pretty confident that the difference you're finding in your sample is a difference that's probably found in the population. You found a real or statistically significant difference. Something everyone likes to find when they have conducted an outcomes research project where you're trying to make a difference. How big of a z-score is big enough? Remember, sample means tend to cluster around the true sample mean, with it being much less likely that the sample means just by chance fall far away. The z-score address gives us the ability to tell just how likely it is that our sample mean happened by chance. So, for instance, a sample mean has only a 2.28% chance of falling greater than 2 z-scores away from the population mean. Whenever your score falls out in those extreme tails, then you probably have a significantly statistical result. Obviously, we want a very low probability that we're wrong. So we're really only interested in differences between our two means that are very far away from each other and have very little chance of being far apart only by chance. For the most part, scientists are willing to take a 5% chance of being wrong. After all, we can't be 100% sure. There is error. Put another way, we want to be 95% confident of our findings. This is where the notion of statistical significance comes in. And all it really is a statement about the probability that we got our results by chance, that the differences in the means of our sample groups isn't what we'd really find if we could measure everybody in the population. So if we want to be 95% confident, then we'll only take a 5% chance of being wrong. In a sense, a significance level of 0.05 means there's a 5% chance we're wrong. A significance level of 0.01 means there's 1% chance that we're wrong. Normally, we write the significance level as p equal 0.05 or 0.01. A significance level of p less than 0.001 means there's less than a 1 in 1,000 chance that we're wrong. Sometimes we need to set a significant level very low, especially if we want to make sure, very sure, that we're not wrong. Perhaps it's a drug that we want to test in a population, and that drug has great potential, but it also has potential for harm. So let's review. We calculate the difference between the means of our two groups. That's the effect of the model. Then we calculate the error associated with that effect. We divide the effect by the error and get a z-score. The z-score is an address on the probability curve and will tell us how likely it is that we see the effect we did purely by chance. If the probability of obtaining that z-score by chance is small, then we conclude the difference between our groups and our sample probably exists in the larger real population. A more formal way to say it is that there's a 95% probability that the true difference in the population is within about 2 standard deviations of our finding. Now, the example I've given you is what you probably use if you were testing for the differences between two means. But there are all kinds of other things we can test. The main thing to keep in mind, though, is that almost all statistical procedures that you're going to come across in this course are simply going to be variations on the same theme. We calculate the effect over the error. It might be a z-score, a t-statistic, an f-value, whatever. And then we figure out what's the probability that we would see that score by chance alone, or a p-value. Where things are going to get a little complicated is depending on things like your research question, what your data's like. For example, perhaps your data isn't normally distributed. We have to select a different type of statistic. How many groups we're comparing. The way we calculate our effect will change. The way we calculate our error will change. The distribution won't always be on a normal curve. So sometimes we'll use a z-score, sometimes we'll use an f-statistic or a chi-square. But remember, all of these statistics are just addresses on a normal curve. It boils down to the simple principle that we talked about in an earlier PowerPoint presentation. As a clinician and as a researcher, you use models to make sense of the real world. In both cases, you determine how well a model fits by comparing what the model explains, the effect, to what the model doesn't explain, error. When reasoning down to individual patients, it's pretty easy to measure the effect and the error, but reasoning them up to lots of people, things get more complicated, and we use statistics to see if our model matches the real world. Now what we're going to do is go through some hand methods of testing a hypothesis, not using SPSS. I want to make that distinction because when you get to the homework, a lot of students confuse the two methodologies. One question is, why do we have to use both? Why don't we just use SPSS to do the homework? Because, as I've tried to point out, this part of statistics is fundamental, testing our sample to the population. It's important to do this by hand so that we can appreciate the results that we'll get when we run SPSS. So, here's the hand process. We state our hypothesis to be tested and we include the alternate hypothesis. We set the level of significance. Typically it's 0.05. We choose the appropriate statistic to test. Might be a z-score, a t-test. We'll get more into that in our next topic. We compute that test statistic. We determine the value needed to reject the null using the appropriate critical values table in the appendix of your book. This would be a good time to check the appendix for those different tables. We compare what we calculated, known as the obtained value, to the critical value that's on those tables. Here's the part to remember. If the obtained value is greater than the critical value in that table, you reject the null. This means that your results are significant. If the obtained value is less than the critical value, you fail to reject the null. Your results are not significant. In the example that we're using, our diet doesn't work. Before we go any further, we have to explain three concepts: type 1 and 2 errors, 1 and 2 tail tests, and degrees of freedom. What is a type 1 or a type 2 error? Whenever we compute a statistic, we can never be 100% certain of our results, even when we do everything we can to reduce error. Remember we talked about selecting a valid and reliable measuring tool? We talked about making sure our sample represents the population from which it's drawn. We want to make sure that our sample is a normal distribution, and we learned how to do this when we run descriptive statistics. From the descriptives, we can now select the appropriate inferential statistic, meaning we will infer our results to the larger population. Even then, there's still a chance of an error. We must set the amount of error that we're willing to accept. For some tests, we can accept as much as a 10% error. For some, it's 5%. For some, it's 1%. Even with a very tiny alpha priori of 1%, and even with significant results, we could still have a type 1 or a type 2 error. In a type 1 error, we think our result is significant when really it isn't, and we fail to reject the null. In a type 2 error, we don't realize that our results were significant, and we believed that our null was true, that there was no difference. I had a friend in college who was doing a rat study. He was testing whether or not different forms of the same vitamin would be absorbed differently in two sets of rats. He fed the two rats, the control group, one type of vitamin, we'll say vitamin X, and he fed the other group the same vitamin in a different chemical form, and then he began to measure it in their feces and urine. And this went on for several weeks, and at the end of his study he found out that there was no difference in the two samples, and so he thought that he had no result. He sacrificed his rats at the end, as you typically do in these studies, and he found that a number of the rats in the experimental group had tapeworms. So he made a type 2 error and had to start over with his study. This time he made sure that he gave all the rats a worm treatment. So just giving you an example of what you might run into. Let's put this another way using the example that we've introduced here. Let's say that we calculated the dependent samples t-test for the end-stage liver disease ammonia levels before and after the diet. We compared our t-statistic to the table in the back of your book and found the obtained value was greater than the critical value in the table. We reject the null. Our results show the diet works. The ammonia levels were significantly different before and after the diet. However, there are other factors that impact ammonia levels in end-stage liver disease patients. If we haven't controlled for these factors, or our sample size is too small, say less than 30, we could have a type 1 error. The diet really would not work in the general population, even though it worked in our sample, or appeared to work. Or the obtained value is less than the critical value on the table, so we fail to reject the null and conclude that the diet doesn't work. Maybe it really does, and we've made a type 2 error. One more thing, as Columbo would say. In our liver disease example, we stated our null. There would be no difference in serum ammonia levels before and after consumption of a branched-chain amino acid diet. The alternative said there would be a difference. This is an example of a non-directional hypothesis. I told you we'd get back to it. We've stated in this hypothesis that there will be a difference, but we've not stated the direction that difference will take. Will the ammonia levels go up or down as a result of the diet? In a directional hypothesis, we would have said it this way. There will be no decrease or increase in serum ammonia levels before and after the consumption of a branched-chain amino acid diet. Or the research hypothesis would state there will be a decrease or increase in serum ammonia levels. Now I'm going to go with decrease because of what I know about the research in this area. Again, we can only choose a direction if we have some idea from the research as to what that direction might be. Based on the direction, we select a one-tailed or a two-tailed test. We use a one-tailed test of significance for a directional hypothesis. This means the significant value can only occur in one end of the curve, either on the left side, where it's negative, or the right side, positive. This test is far more powerful, so if you can, always write your hypothesis in a direction. If you really don't know, if the research is sort of mixed in your area of interest, then use a non-directional. When we use a non-directional test, we must use a two-tailed test of significance because the value could occur on either end of the curve. We could have a positive or a negative result. We fail to reject the null hypothesis when the test statistic falls in that blue region. The test statistic likely occurred by chance. We reject the null when the test statistic falls in the black region. It is not likely the statistic occurred by chance alone. This is the same step as comparing your obtained value to the critical value in the back of your book. And just one more thing. Degrees of freedom. Imagine a set of 3 numbers whose mean is 3. There are lots of sets of 3 numbers that have a mean of 3. But for any set, the bottom line is this. You can freely pick the first 2 numbers, any number at all. But the third and last number is out of your hands as soon as you pick the first 2. For example, 1 plus 6 plus 2 is 9, and the mean is 3. We had no choice to select the number 2 after 1 and 6 were added. When we compare an obtained value to a critical value, we have to include degrees freedom. Degrees freedom is always the number in our sample minus 1. This is important to remember. It can be a little difficult to explain degrees freedom, and we'll try to do this again and again as we go through with each statistic. But for now, remember that it's the number of a sample minus 1. Now back to the steps of testing a hypothesis by hand. Remember what those 6 steps were. So we state there is no difference in serum ammonia levels before and after consumption of branched-chain amino acid protein in patients with end-stage liver disease, and our research hypothesis says that there will be a difference. We set our alpha priori level at 0.05 because we have chosen a non-directional hypothesis, and 0.05 is an acceptable amount of risk that we're willing to take. In this case, we will use a dependent samples t-test because we're testing the same people at 2 different points in time. I don't expect you to know that right now. In our next module, we will talk about the t-test and we'll get into selecting the right statistic. We calculate the t-value and it comes out to 5.39. Now this is a non-directional hypothesis, so we will use a 2-tailed test with degrees freedom of 60. There were 62 people in the sample, but we're going to choose that value that's closest to 60 based on that table on page 354, 355 in your book. And if you look there, you'll see the critical value is 2.001. So we reject the null. We are 95% confident there's a significant difference in ammonia levels before and after the diet. If you are looking at the table in the back of your book, I found one similar to it. First thing that we do, since our hypothesis is non-directional, we're going to select this 2 tails. And that would look at this lower level here. We've checked the 0.05 alpha priori level. Our degrees freedom column is here. We come down to 60 because that's closest to our sample size of 62. And we read across where these 2 columns intersect, and we see that our critical value is 2.001. And so we know that we have significance. Why don't we use SPSS to test a hypothesis? It's much easier, and we're going to do this in the next topic that we cover. Instead of telling you if your obtained value is more or less than a critical value, SPSS will generate that t-value, or whatever statistic you choose. It will automatically figure the degrees of freedom, and it will provide the significance level known as the alpha or p-value. A p of 0.05, as we said before, means there's a 5% chance that the results occurred by chance alone. Small p-values are what you're after, because they indicate the null hypothesis should be rejected. The results did not occur by chance, and you can infer those to the general population. Large p-values mean that your results occur closer to the mean and by chance, so we fail to reject the null. So the results from our ESLD diet study might be written like this. There was a significant difference between the ammonia levels at baseline and at follow-up of ELSD patients consuming a diet of 60% branched-chain amino acids, where T equaled 5.39 and P was 0.02. T is the test statistic that we chose. 62 is the number of patients in the study, and P is the significance level. So that's the difference between conducting the same test in SPSS versus the previous slides where we do it by hand. That's all.